So we'll move on to cosine. Cosine will be the next one. Now if you remember cosine is the x-coordinate. So we're graphing theta versus x. So x is going to be on the vertical, theta is going to be on the horizontal. And if we take the inversion, theta will be on the vertical, x will be on the horizontal. So this is going to be x equals to cosine theta, and then theta is equal to inverse cosine of x. Okay, so if you remember the graph for cosine, let's go from 0 to 2 pi. Cut this in half, so halfway is pi. Take these two and find the middle, that's pi over 2. You take the right 2, find the middle, it's 3 pi over 2. Generally, that's where the middle's at. Cosine ranges from -1 to 1, just like sine does. But the starting point's different. Starting point for cosine would be 0, 1. Next is pi over 2, 0. Pi, -1. 3 pi over 2, 0. And then 2 pi, 1. And then we'll draw the pattern for cosine. Looks something like this. That looks kind of ugly. See if I can try to fix that a little bit. Okay, so there's one period for cosine, and let me draw that one period, but inverted to the right. So here, if I try to draw the inversion, the x-coordinate ranges from -1 to +1. 0's here, 2 pi's up here, pi's down here, pi over 2, 3 pi over 2. And if I do this correctly, cosine starts up at 1, at 0, 0 here, -1 here, 0 here, and then 1 here. So it's kind of strange, unless you're very familiar with the graphs and are okay with thinking of them inverted. So that's what the inversion of cosine looks like if I draw it over one period from 0 to 2 pi. So hopefully that's not too hard to wrap your mind around. Problem with this though is that there's too much. Cosine, what I've drawn so far, the restriction from 0 to 2 pi is not 1 to 1, and its inversion is not a function. So we cut off a certain piece to make sure that it is. So the piece that we cut off would be the right half, the stuff to the right of pi over 2. So that's the stuff above, or not to the right of pi over 2, to the right of pi, or further past pi. So up to pi, we stop it there. And this little chunk here is 1 to 1 now. So what does that correspond to on my unit circle? So what piece of the unit circle is that? We're talking about everything between 0 and pi. So 0's here, pi is here. We're talking about the upper half. So all of this stuff. So for cosine inverse, it's the upper half, the top half. Whereas sine, it's the right half. And that's our definition, or that's our visual definition for inverse cosine. So here we have written in mathematical terms, it's from 0 to pi. And if theta is equal to inverse cosine, then y is equal to cosine theta. Tangent. That's going to end up equaling to the right half just like sine. Tangent and sine are odd functions, so they're going to behave the same way. We'll just take everything that's centered around the origin from negative pi over 2 to pi over 2. So for tangent, we're going to do the right half stuff. Now the nice thing is, tangent takes on a full period on the right half of the circle. So let's say this is negative pi over 2. This was positive pi over 2. You should remember from chapter 6, sections 5 and 6. That's where the asymptotes for tangent are. The two major asymptotes. Remember, it's pi over 2 plus n pi. That's 0, This is negative pi over 4, positive pi over 4, and we get 1 and negative 1. You guys remember all that stuff. So it's 1 at pi over 4, negative 1 at negative pi over 4, 0 at 0, and it does this. And it goes on forever that way. This one goes on forever this way. And there's our graph for tangent. So what that's going to look like as an inversion, this is theta, and this is, we'll just call it y. Y is here, and this one's theta. It's not exactly the y coordinate, it's the ratio of the y to the x, so y over x. But I'll just call it y, not a big deal, it's just a number. So then theta ranges from negative pi over 2 to positive pi over 2. And we have asymptotes that are now horizontal as opposed to vertical. And we're trying to fit all this information this way. So it's going to be pi over 4 here, 0, negative pi over 4 here, 0, I might want to draw this in blue, no? Let's see. So 0, 0, let's say 1 is here, negative 1 is here, and the graph looks like this, where it's going to do this, and this. Okay, so then we look at both the original graph and the inversion of the graph. And the question is, do I have to cut anything off? The answer is no. I don't have to cut anything off, because both of those functions are one-to-one, or both of those curves correspond to one-to-one functions. So because those are both one-to-one functions, I don't have to cut anything off. Earlier I had to cut stuff off because those were not one-to-one functions. But here I don't have to cut anything off at all because those pass both the vertical and horizontal line test already the way they are. So what we're actually cutting off though are the other periods to the left and to the right of those main asymptotes. So we did have to cut stuff off, and I only chose to graph stuff between negative pi over 2 to pi over 2. And that should be good enough though. So the key distinction here, the main takeaway, inverse sine and inverse tangent are on the same definition for theta, the right half of the circle. Cosine is the weird one. Cosine is the one that we define differently. It's from 0 to pi, so the upper half instead. So we're going to remember that when we're calculating these things in the next example. So we'll look at example 2. So for cosine, cosine inverse of negative 1. So again, these are supposed to be thetas. There's a typo. Those are all supposed to be thetas. So cosine, if you remember, we're looking for the y coordinate. Or those are y coordinates, by the way. For tangent, that's what tangent is equal to, so we call that y over x, basically, because tangent is y over x. So if I finish that off, y is equal to cosine theta. So y is equal to cosine theta. That's the way we think of it. So if I look for letter A, we want theta equals to arc cosine of negative 1. We're literally looking for the angle theta that makes cosine negative 1. So cosine, if you remember correctly, is the x coordinate. So x is equal to cosine theta. We're talking about the right half. So, or sorry, not the right half, the upper half. So where on the upper half is the x coordinate negative 1? That's going to happen here. So that's negative 1 comma 0, and that's exactly what we want. Negative 1 for the x coordinate. So what's that angle there? 180 degrees or pi. So the answer for letter A is literally pi. And that's it for that one. Now the next one's a little bit tougher. They want where the y coordinate's equal to negative square root of 3 over 2. So we're thinking of a y coordinate. Negative square root of 3 over 2 is this point right here. So negative square root of 3 over 2 is the, not the y coordinate, sorry. And I wrote y coordinates here. Sorry if that was confusing. These should be x's. And it's because I wrote y's out here initially where the thetas are supposed to be. So those are x coordinates, my bad. So the x coordinate is negative 3, square root of 3 over 2. So negative square root of 3 over 2, this is comma 1/2, I think, if you know your unit circle. That happens where? That's going to happen at this angle from here to here. Theta is equal to 5 pi over 6, if you remember correctly. Because this right here was 30 degrees away. 30 degrees is the same thing as pi over 6 radians. So that's 5 pi over 6. So then the answer for letter B is 5 pi over 6. If you have your unit circle ready or handy, you're literally just looking for the angle that makes the x-coordinate negative square root of 3 over 2 on the upper half. Now let's try this for arctangent. Letter D. So arctangent of square root of 3 over 3 is the angle theta that makes tangent of theta, square root of 3 over 3. So square root of 3 over 3 is equal to tangent theta. So what's theta is what we're looking for. That's a bit more complicated, and let me see if I can try to call back some mathematics that we saw in previous sections. So first off, square root of 3 over 3 comes from the rationalization of 1 over square root of 3. That we should know. So square root of 3 over 3 came from the rationalization of 1 over square root of 3. That's the first argument. Second argument, tangent, the ratio 1 over square root of 3, comes from dividing the x-coordinate and the y-coordinate. So this refers to a special angle, and there are special angles which there's a square root of 3 for. Square root of 3 shows up as a square root of 3 over 2. The y-coordinate or the x-coordinate, the opposite coordinate, shows up as a 1/2. So this was probably because we were dividing a 1/2 by a square root of 3/2. And the 2's cancel to a 1 over square root of 3. So where do we have a 1/2 for? This was a sine, right? Sine theta is on top, and a cosine theta equal to square root of 3 over 2. For what angle does that happen, where sine's 1/2? Isn't that where theta is equal to pi over 2? Or sorry, pi over 6. So that's this point right here. Square root of 3 over 2, comma 1/2. This right here is 30 degrees, or pi over 6. And that's how we figure out that part. Now, of course, that's trying to reason mentally instead of using a calculator, which if your calculator can spit out radians in terms of pi, then it's going to be easy to just type that in and get that, no problem. So that's example 2. Understanding the domain and range for inverse, sine, cosine, and tangent. First step. So what we'll do is we'll take that further and look at more complicated expressions. So before we look at example 3, here's an algebraic fact. So if you have functions that are 1-to-1, so f we're going to say is a 1-to-1 function, then we have this expression here. F inverse of f of x is equal to x, and then f of f inverse of the y-coordinate is equal to just the y-coordinate. And we're restricted, of course, to the domain d of f and the range r of f for x and y. So let me see if I can make sense out of both of those statements. Actually, I should have left those boxed. So how do we make sense out of both of those statements? The whole idea is that these are functions that transform an x-coordinate to a y-coordinate and backwards, vice versa. So to go from an x-coordinate to find its y-coordinate, you plug it into the function f. So to find y is equal to f of x. That's the functional relationship between x and y. You plug in your x-coordinate to the function, and you get the y-coordinate. Now, this also works backwards. If you plug in the y-coordinate into the inverse, you get your x-coordinate. So x is actually equal to the inverse function applied to y. So x is equal to f inverse of y, and then y is equal to f of x. Those are both true. So if you check this first box, then that's going to be obviously true if you follow the diagram in the order direction, or the arrow direction. So you start off with x. In this first one, you start off with x, you plug it into f, you get y. Then you plug in whatever you get into the f inverse, and you go back to x. It's a cycle. This one is the exact same thing, we're just starting at y instead. So we start with the y-coordinate instead. You plug it into f inverse, you get x. You plug that into f, and you go back to y. So it's a cycle. That's all that means. If you have 1-to-1 functions, that function and its inverse have a cyclical pattern to it, and the cyclical pattern is given by this diagram. So that diagram is pretty important. That's also true for any individual function and inverse function pairs. So for sine and inverse sine, that's also true. If you take the inverse sine of sine theta, it's equal to theta if we restrict ourselves to the right circle. If we're not restricting ourselves to the right circle, it gets a little bit more complicated. Also true if I do it in this order. Sine inverse, sine of sine inverse of the y-coordinate will give me the y-coordinate as long as we're plugging in a number between -1 and 1 for the y-coordinate. So we have to follow, of course, the domain and the range properly in order for that to work out. And it's also true for cosine inverse of cosine, cosine of cosine inverse, tangent inverse of tangent, and tangent of tangent inverse. They invert each other as long as you play by the correct rules that were in the upper half for cosine or the right half for tangent and sine. So we're going to use that fact to look at example 3. So I'll be flipping back and forth between these things to make sure that we're getting this done right. So let's look at sine of arc sine of 1/2. So it's the same thing as sine of inverse sine of 1/2. So 1/2 is the y-coordinate. So here's the idea. We check, is 1/2 between -1 and 1? Because it's a y-coordinate. So we check for this thing right here. Is it a y-coordinate between -1 and +1? Yes, it is. So if that's the case, then those two just cancel each other out and you're left with 1/2. That's the answer. So they should cancel each other out as long as this number is a nice number. And by nice number, it follows what we circled over here. It's in that, it satisfies that condition. So yeah, check mark for that one. Letter B, cosine inverse of cosine. I'd like for those two to cancel out, but in order for them to cancel out, we check the value of 5 pi over 4. So because it's the order of inverse then no inverse, we're talking about this one right here, and this rule must apply. Theta must be between 0 and pi. So is 5 pi over 4 between 0 and 2 pi? Or sorry, not 2 pi, pi. That's the question. So how would I graph 5 pi over 4? And that's probably where I need the circle to help me out a little bit. So pi over 4 is where? That's this thing right here. 45 degrees, same thing. Why am I asking that question? What's pi over 4? Because 5 pi over 4 is 5 of those. That's 1, 2, 3, 4, and 5 would give me here. So this is 5 pi over 4. Is that in where we want it, between 0 and pi? The answer is no. That's outside of the upper half. That's in the lower half. So then this does not simply cancel out to 5 pi over 4. So the answer is not 5 pi over 4. We were kind of hoping that that was going to be the case, but that's not the case. So no. Then I have to be careful. Then I'm going to use the circle to figure this out piece by piece. Cosine inverse of, then I got to figure out, well, what's cosine of 5 pi over 4? So then we do this step by step. What is cosine of 5 pi over 4? If you remember, cosine is the x-coordinate. What's the x-coordinate of 5 pi over 4? Negative square root of 2 over 2. Y-coordinate is negative square root of 2 over 2 as well, because it's corresponding to this point over here that is square root of 2 over 2, comma square root of 2 over 2. So that's just a 45-degree angle, but in the third quadrant. And because it's third quadrant, it's negative. So the answer here for the inner portion is negative square root of 2 over 2. So that's the first piece of this particular problem. So that was this angle from here to here. That's theta. Then we're trying to find the inverse cosine of negative square root of 2 over 2, which I can actually calculate that because negative square root of 2 over 2 is between -1 and 1. There's a place on the upper half of the circle where that happens. So on the upper half of the circle, where cosine is negative square root of 2 over 2. Negative square root of 2 over 2 happens here as an x-coordinate. And as a y-coordinate, it's positive square root of 2 over 2. So we're talking about this angle here. And we're really looking for this x-coordinate. So what x-coordinate is that? Actually, no, we're not looking for that x-coordinate. We're looking for the theta angle. So what angle is this? That angle is 3 pi over 4. If you remember, this was 1 pi over 4. This is 2 pi over 4, and this next one is 3. So it's a little messy, but that's how it works. So then this was 3 pi over 4. We try to do this with the next problem. Arc, tangent, and tangent we hope cancel out, but that's only going to be the case if this angle is between negative pi over 2 and pi over 2, which I don't believe that's the case. Negative 5 pi over 2 is a very big angle. It's outside of that range. So I'm going to erase all this, which if you wanted to see what that was again, you could just go backwards into the video. So where is negative 5 pi over 2? So first off, we disregard the 5, and I'm going to think in terms of pi over 2's. So pi over 2 is a 90-degree angle. This is pi over 2 from here to here. So 90 degrees. So then this is, we're thinking about negative. This is negative pi over 2. This is negative 2 pi over 2. You go backwards this way further. This is negative 3 pi over 2. This is negative 4 pi over 2. And then we finally get negative 5 pi over 2 out here. So negative 5 pi over 2 would be here. So that took a little bit of a rotation to find out where that was going to be. So then I want those x and y coordinates. This is 0, negative 1. That's x comma y. So if you remember, to find tangent of that angle, negative 5 pi over 2, you just take the division of the y and the x in that order. So you divide y by x. So in this case, that is negative 1 over 0. This is undefined. So no, I can't take the arctangent of an undefined quantity. It's not going to work. And that's it for example 3. So then we'll move on. We'll look at example 4. More complicated expressions. Now we could think of this in terms of a circle, but sometimes circles aren't going to be helpful. These can be done using a triangle. So evaluate each expression without using a calculator. Sine of cosine inverse of 4/5. So sine of cosine inverse of 4/5. What you're gonna, the way that I would suggest you start off is you write sine of theta. Every time you see an inverse trig function, it's calculating an angle theta. That's the way they taught you in geometry, or that I taught you at the beginning of the trigonometric stuff, is if you're solving a right triangle, the angle is going to be found by using an inverse trig function. So inverse trig functions, geometrically, are looking for angles. So then, what I do then is I take theta equal to cosine inverse of 4/5. That's the substitution. Now if you go a little further, theta is equal to cosine inverse of 4/5 means that cosine theta is equal to 4/5. So that's what I'm establishing. Theta is the angle that makes cosine 4/5. Then I want the sine of the same exact angle. So if I'm thinking of the differences between sines and cosines for the same angle, I'm going to draw a right triangle. So let's say this is theta. And they said that cosine's 4/5, which means that's the adjacent divided by the hypotenuse. Adjacent measures 4, the hypotenuse measures 5. What does that make the opposite? Well, if you know your special right triangles, this is a 3. 3, 4, 5. That's because 3 squared plus 4 squared is equal to 5 squared. 9 plus 16 is equal to 25, basically. So then we want sine. Sine of theta is just equal to the opposite over the hypotenuse, 3/5. And that's it for this problem. Which these are kind of simple if you use a right triangle. So then we do this again, but for this particular problem. What's cosine of arcsine of 8/17? So again, you draw a right triangle. 8/17 is the value of sine of the angle theta. So if theta is an angle, sine of that angle is 8/17. I'm going to call this theta. Sine is opposite over hypotenuse. So then we want the adjacent for cosine. So cosine is literally just equal to the adjacent over the hypotenuse, 17 in this case. So if you know your special right triangles and you're really good at Pythagorean triples, actually no, I don't even want to say, I will, because I might embarrass myself, but I think this is 15. We've seen a problem with those numbers before, and I believe it's 15. So what's the reason why? 8 squared is 64, plus something squared, so this is something squared, is equal to 17 squared. And if you remember, 17 squared is 289. You can verify that on a calculator. But I think there was a video that I did where I kind of painfully went through that calculation. 17 squared is 289, so I still remember that. It's 289. And if I subtract 64 from 289, you actually get 225, which I understand is the square of 15. So that's what's missing, 15. So then cosine theta is 15 over 17. And that's how you do that problem. So it's as simple as that. So if they gave you something like this where you have trigonometric functions that don't match, sine and cosine, let's say secant and tangent, cosine and cotangent or something like that, draw a right triangle and it should make it a lot easier. Which that's the exact same method that we're going to use for the next problem. So we'll look at the next problem, example 5. And for example 5, evaluate each expression without using a calculator. Letter A, sine of arctangent of 4 over 3 minus arc cosine of 12 over 13. So now it's getting more complicated on the inside. So here's the idea. Everywhere you see an arc or an inverse of a trigonometric function, that's an angle. So I'm going to call this one theta. And maybe I don't want to use theta and another Greek symbol. Maybe I'm going to call this A and this one B. So that way this is sine of A minus B. And there's something that we've already seen, but in a previous section. So sine of A minus B, if you guys remember correctly, there's a formula for it. Sine A, cosine B. You keep the sine, cosine A, sine B. So then I got to figure out what sine A, cosine B, cosine A, sine B are. And for that, we need two triangles. First triangle is the one with A in it. Second triangle is the one with B in it. Okay, so in the first case, A has a tangent of 4/3. Tangent is opposite over adjacent. This is a 3, 4, 5 triangle. Now in the other one, B is cosine. Cosine of B is 12 over 13. Cosine is adjacent over hypotenuse. I didn't draw it to scale basically, but either way. So what's the other one? I want to say that this is a 1. That's another special right triangle, but we can try. So this one is the square root of 13 squared minus 12 squared. Pythagorean theorem. 12 squared plus this one squared is equal to 13 squared. So if you subtract 12 squared from 13 squared and square root it, you get the missing 1. So that's square root 169 minus 144. And if you subtract those, you get, crap, that wasn't 1, so I embarrassed myself already. 169 minus 44 is 25. It gives me 5. So yeah, this one was a 5, not a 1, my bad. I don't know all of my special right triangles. So it's a 12, 5, 13 special right triangle. So then using this visual, we can fill this up, no problem at all. Sine of A. Sine of A is opposite over adjacent on the A triangle, so 4/5. Times cosine of B, 12 over 13, minus cosine of A, 3/5, times sine of B, 5 over 13. And we're almost done. All I got to do is simplify this expression. 4 times 12, oh crap. So now we got to multiply. 4 times 12 is 48. 5 times 13, 65. Minus 3 times 5, I know that one, 15. And then 5 times 13, 65 again. And we subtract 33 over 65, I believe. So 48 minus 15, let me just double check. That is 33, yeah. So 33 over 65, I don't think I can reduce. 33 is just 3 times 11. Both of those are prime numbers. 15 is 5 times 13, and both of those are prime numbers. Neither of those are overlapping, so it's just that. They don't have anything in common. And that's it for example A. Example B, you do this in a similar manner, except that it looks a little weirder. 2 times arc sine of 8 over 17. What you do is you take arc sine of 8 over 17 as an angle. We'll call it theta. And if that's the case, then sine of theta is equal to 8 over 17. And this is a separate problem than this stuff. So I'm going to separate those like that. So sine theta is 8 over 17. If that's the case, I'm going to draw a right triangle. Call this theta. And that's 8 over 17. And is that one 15 here? That was the same triangle as the one before. Okay, so what we need to do is simplify this expression, cosine of 2 theta. And if you remember, that's the one that has 3 different versions. Cosine squared minus sine squared, 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. So you can take your pick. Let's say I didn't do this right, the 15, so I want the one with only sine. 1 minus 2 sine squared theta. That's one of the 3 different double angle formulas for cosine. So then we just plug in what the value of sine was. 1 minus 2 times sine. Sine was 8 over 17. And I got to square those numbers. But oh well. 1 minus 2 times 64 over 289. 1 minus, well, 2 times 64 is 128. And then over 289. Then I got to subtract. So 1 is the same thing as 289 over 289 minus 128 over 289. Do I have to carry over anything at all? Let's see. 161 over 289. And I think that's it for this particular problem. That's example 5. And that's the hardest stuff that you're going to see for this particular section, is thinking in terms of right triangles like that and plugging into a sum, difference, double angle, or maybe even a half angle formula. And that's basically it for this particular section. There's another problem here that I added in there, which kind of leads into the next section, so I do want to go over those. And this is going to require a calculator. So for this, you're going to want a calculator. You can either use your own if you have one, like a TI-84, TI-Nspire if you have your own, or you can go to a calculator online. And the calculator online that I would actually suggest, if you don't use emulators and stuff like that, there are free emulators for TI-84s, TI-89s, TI-Nspire. I don't know about TI-Nspires. I've never found free ones for those. There's probably free ones out there, but I've never had to download one of those because I get that software as a teacher. But the one that I would recommend would probably be Desmos, www.desmos. Actually, I'm not sure what the website is. I would just Google Desmos as a word. So DESMOS, and then I would type in the word calculator as well. Google it. It's going to be like one of the first things, and you could plug these things in. So there's a way that you can type it in, but it's pretty user-friendly. You should be able to figure it out no problem. So on a calculator, we'd like to solve these things. Now, we're going to do some manipulations by hand first. If you look at this first one, that should be letter A, by the way. So that was a bit of a typo that I didn't get to fix. This was a bunch of typos because I just typed this thing out recently. And usually the first few drafts have typos. So I'm going to have to fix all that stuff for later on if I'm going to use this in class, maybe in future years. But either way, so for that first one, 2 sine theta plus 1 is equal to 0. You can subtract 1 on both sides, and you get 2 sine theta is equal to negative 1. Divide by 2 on both sides, and you get sine theta is equal to negative 1/2. Now, if you plug this into a calculator, sine inverse of negative 1/2 is what you would plug in. So sine inverse of negative 1/2. But we already know that one in our heads. This is negative pi over 6, I hope you remembered. The reason being is because sine inverse of 1/2 is pi over 6. The negative would just correspond to negative pi over 6. So if I drew that here, pi over 6 is where the y-coordinate is equal to positive 1/2. I don't want positive 1/2. I want negative 1/2. So that's going to be this angle here. Negative pi over 6 if this were 1/2 negative. So I'm going to disregard this one because that's not part of the solution. That was just part of the process for me to find the solution, but it's not actually a solution. So this is one of the solutions, and that's a x-coordinate, or sorry, not an x-coordinate, a y-coordinate of negative 1/2. So the angle is negative pi over 6. That's one of my answers. So I'm going to box that. Theta must equal to negative pi over 6. Now, if I had read this, solve for all values of theta on the circle from 0 to 2 pi. So is this the only one? Is this the only place on the entire circle where the y-coordinate's equal to negative 1/2? And the answer is no. What you do is you extend this horizontal line all the way out this way. So there's usually a line that's going to give you 2 intersections. So for most of these problems, there's going to be 2 answers. So there's a second answer where the y-coordinate is also negative 1/2. So if you remember, sine is negative in 2 different quadrants, the 3rd quadrant and the 4th quadrant. So you're obligated to find both answers. So answers in both quadrants. So then if that was negative pi over 6 out here, which by the way, I can't write that as negative pi over 6. The calculator is going to give that to me as negative pi over 6. But negative pi over 6 is not on the circle from 0 to 2 pi. So I have to change that to a value that is in the circle from 0 to 2 pi. So that's negative pi over 6 that way. But what's the actual way that I write that? You write it this way. So from here to here, all the way out this way, is 11 pi over 6. And then from here to here for this guy out over here, I believe that one's, I was going to say 5 pi over 6, but that's completely wrong. 7 pi over 6 is the other. So then we have 2 answers, one at 7 pi over 6 and the other at 11 pi over 6. So then a very, very common question that should pop up in y'all's heads, how come here I have to change the negative pi over 6 to an 11 pi over 6, and before, let's say example 1, I think it was example 1, right? Or example 2, and I think it was example 1. Here. So I think we had the exact same question in example 1. Sine inverse of negative 1/2, and we kept it as negative pi over 6. Basically, what we're asking here, this is a much less complicated question. The question is, what would the calculator spit out if you plugged in negative 1/2 into a sine inverse? It would give you negative pi over 6. So this one's much simpler. It's just asking, what does the calculator give you? That's literally what the calculator gives you. All right. So if I'm trying to solve an equation where they manipulated the domain, they want answers to be in a specific domain. It has to be a number between 0 and 2 pi. So then I have to fix the negative pi over 6, which isn't wrong. The only reason why we consider it wrong is because it's not inside this interval. It's outside that interval. So we have to change it into a number that's coterminal with that one. So that way that number is in that interval from 0 to 2 pi. So 11 pi over 6 and negative pi over 6 are coterminal. So they're equivalent with regards to a tangent function. But that's in the format that they want it in. They want it on the primary circle 0 to 2 pi. That's the reason why. So we do this again for 5 cosine theta equals to negative 7, or sorry, minus 7 is equal to 0. So what you would do is you would add 7 both sides. So 5 cosine is equal to 7. You divide by 5, cosine theta is equal to 7 over 5. What I'm going to do is on a calculator, I'm going to type in, and the problem with this particular recording software is I can only do one screen at a time. So I'm not going to be able to switch to a calculator without having to stop the video, re-record with the calculator, and then stop video and then start re-recording with the notes again. So because that's annoying, I'm not going to show the calculator. But you would take the inverse cosine, type in 7/5, and then see what it gives you. And in this case, this one's undefined. The reason being, 7/5 is bigger than 1. So this one's undefined. And I think that's just a mistake on my part. I just typed in random numbers, or that I just came up with, and that was supposed to work as opposed to being undefined. So this is something that I just typed in and didn't even think whether or not it was in the domain that it was supposed to be. So I'm going to change this problem. So let's switch this to a 5 and this to a 7. So that way it is in the proper range between negative 1 to 1. So if you do that, you get cosine theta is equal to 5 over 7. So I didn't expect that. That's my bad. So cosine theta is 5 over 7, let's say. So I'm going to switch those numbers. And then you take the inverse cosine of 5 divided by 7. and it's going to give you, I think mine's in degrees right now, and I need to change it back to radians. So let me see if I can do that really quickly. Yeah, it was in degrees. Now I'm changing it to radians. Let's go back, retype this, inverse cosine of 5 over 7, and I get this number. So if you take inverse cosine of 5 over 7, that's supposed to be theta, and you get a number 0.775193 something something. So that's about 0.78. So it's about 0.78. So what you do is you remember cosine is an x-coordinate. This was a positive x-coordinate also, and we're talking about values in the upper half. So this was 0.78. 0.78 is somewhere really close to 1. So 0.78 is here. That's the x-coordinate. We're talking about this angle here. This is theta. Oh no, wait, hold on. That's not right. So first off, 5/7 is approximately how much? So 5/7 is approximately, and I gotta erase that, because this is theta, this is the angle. 5/7 is approximately 0.71428 something something. So that's about 0.71. So the x-coordinate is 0.71, which is still about the same place. We're talking about this. That x-coordinate, theta, was 0.78. So that's one of the answers, by the way, because that's between 0 and 2 pi. I want another place where cosine is the same x-coordinate. Now, because we're talking about the same x-coordinate, what we do is we consider we continue that line that we drew. It's a vertical line now, and we draw this angle that makes this line this way. So then we want this angle in radians. So this theta is equal to how much? So that's the idea. So what we do is, well, this way from here to here is another 0.78. It should be symmetric and identical to the other angle up there. So if that's 0.78, then this theta is 2 pi minus 0.78. And this is why I included problems in here like this for this particular section, because we're going to be needing to do this for the next section. So what is this 2 pi minus 0.078? So what you do is you type in 2 times the pi symbol. Let me find my pi symbol. I forgot my pi. Where's it at? Oh, there it is. 2 times pi minus 0.78. And you get 5.503185-ish. So something like that. So then the other theta is 5.50. So there's always 2 for these linear questions. And that's how you use the inverse to find solutions to these types of equations. So that's going to be it for section 5. The next video will cover the topics for 7-6, which are equations.